We are all waiting for this moment. Now, this is the time. Welcome to the live discussion session of Vigyan Chacha Asor. We work to spread scientific temper among common people, especially among students. Today, we have Professor Saptarshi Basu from the Indian Institute of Science with us. He will speak on different avatars of droplets. Saptarshi Basu completed his PhD from the University of Connecticut in 2007 before joining the University of Central Florida as an assistant professor. In 2010, he relocated to India and joined the prestigious Indian Institute of Science in Bangalore, where he is the INAE and KSIIDC chair professor in the Department of Mechanical Engineering. Basu primarily works on multi-phase systems, especially droplets at multiple length and timescales across multiple application domains, ranging from surface patterning to combustion. He has completed extensive research on the transmission of aerosols relating to COVID-19 and on the efficacy of face mask. His research marries fundamental aspects of classical fluid mechanics like vortex dynamics and swirling flows and the more interdisciplinary aspects of interface transport of droplets in multi-phase systems. Basu is a fellow of the Indian National Academy of Engineering, National Academy of Science, ASME, the Institute of Physics, Royal Aeronautical Society and Royal Society of Chemistry. He is the recipient of a DST Swarna Jayanti Fellowship in Engineering. Professor Basu also received the prestigious J.C. Bose grant from ANRF. Professor Basu also received the Distinguished Alumnus Award from University of Connecticut, K.N. Sitharamu Medal and Prize from ISHMT, and Rajiv Goel Prize in Applied Sciences. Basu also is a co-founder of a biotech startup specializing in AI-based point-to-care diagnostic and a technological advisor to a tech startup involved in microgas turbines. Basu serves as an editor or guest editor of several journals, including Scientific Reports, Experiments in Fluid, and European Physical Journal Special Topics. His research is funded by the Department of Defense, Indian Space Research Organization, Department of Science and Technology, Indo-German Science and Technology Center, Indo-US Clean Energy Center, the National Science Foundation, and industries like Siemens and Tata Motors. Additionally, Basu has guided more than 25 PhD students over his career. We are proud to have Professor Basu with us. I will request Professor Basu to start his lecture.
Thank you, Professor Pal, and good evening to everyone in the audience. Though I cannot see you guys, but assume that there would be quite a few who would be listening to this lecture. So today what I'm going to do is that I'm going to give a glimpse of what kind of work we do in our lab primarily, and highlight on maybe 2 to 3 topics which may be of some relevance or interest to a broader community in particular. So as the title of the talk actually designates, it is called the Avatar, the Way of Droplets. So we will see in the next few slides what I exactly mean by that. So it's a multi-scale journey, Multiscale in fluid dynamics essentially means that it is various length scales and time scales. So different times and different lengths involved in the problem. So before I begin the lecture, usually it's customary to, acknowledge all the students, my collaborators, as well as people who have graduated from the lab and are elsewhere as postdocs and faculties all around the world, including India. So I call them my partners in crime because they are really partners, and some of them are much more knowledgeable than I am, especially the students. So all credit of these works actually goes to them. So droplets in our lives. So when we talk about droplets, let us see that, for example, the first few pictures that you see over here is sprays. Sprays is basically a conglomeration of droplets. So it is used in energy sector, it is used in defense, it is used in aerospace, it is used in additive manufacturing. How in additive manufacturing, I will kind of illustrate in a few minutes. And then something called spray coating. This is all what you use to coat materials on the surfaces. Okay, so what you see in these particular videos are basically sprays, cold spray, that means the sprays which are not reacting, then spray flame, the one that you can see over in the middle, and lastly, the last example is a hypersonics application where you can see actually the shock and the flame coming out from the backside of the combustor. These are at the big scales where the droplets have high velocities. But at the same time, when you look at droplets at the very small scales, you look at applications like surface patterning. Now, all of you are familiar with clean room applications where you use soft lithography basically to create different structures on surfaces of different kinds. But how about if you build those structures using a droplet-based framework? So surface depositions, 3D printing, biofluidic assays, these are all part of droplet depositions. And these happens at very small, length scales, time scales, and small velocities also. So that the top row basically designates sprays and droplets at extremely high velocities, whereas the lower part actually shows droplets where the flow is much more sedate. But both involves basically droplets. The physics does not change that much. Moving on, you also have droplets in the framework which we call microfluidics. So this is called droplet-based microfluidics. It has been there, and it is used regularly for point-of-care diagnostics. So microfluidics is a big area of research, and it is advancing every day. So what you see on the right-hand side is an application of the droplets, which we have all encountered about a couple of years ago during the COVID era, where the disease transmission happened through droplets. So when you coughed, sneezed, or talked, you generated droplets, and these droplets traveled in the air and infected persons who are located far away from you. So this is the disease transmission. One example is COVID. It can be any other disease transmission as well. Anything that is respiratory can actually happen in this particular fashion. Then moving on, you also have droplets in agriculture, what we call precision agriculture these days. So they also involve transport of droplets, basically droplets which can get pesticides or nutrients. And droplets are transported by sprays or by vortex rings to transfer them to targeted plants. Is that the droplets are there everywhere, and it's not just in one particular application domain, it's spread across multiple application domains. All right, so now a little bit technical. The fluid dynamics is all about identification of the scales of the problem. So fluid dynamics is basically Newton's law. So it all depends that what are the velocity scales and the time scales of the problem. So there comes the interesting part. So what you can see over here, the velocity scale increases from left to right. So at very low velocity scales and very low length scales, you have flows in microchannels You have droplets which dries on surfaces. For example, the one on the top, you can see the bacterial flow in a microchannel, and one at the bottom, you see a drying droplet of blood. So these are at very low velocities of the order of microns per second, and the length scales are usually anywhere between 1 micron or 2 microns all the way up to hundreds of microns. In the middle, now if you go to moderate velocities and small to moderate length scales, you have droplets which basically impinges on surfaces, droplet impact scenarios, then droplet impact on masks and wear meshes, droplet which comes out of your eye, the droplet vortex interaction, your soap bubble problem, and all these phenomena. These happens at moderate velocities and still small to moderate length scales. Okay, so these are right there in the middle. And if you want to ask that where the droplet impact scenarios are used, you can readily see, for example, your windshield of your car. It is usually made out of a hydrophobic coating so that the droplet impinges on it and basically rolls off. But there are other applications where you actually might need the droplet to stick onto the surface. So the surface engineering or the surface chemistry and the droplet impingement plays a significant role in all those applications. The one that you see in the middle, which is where there is a human eye that you can see, this is what we call a glaucoma testing. This many of us have done, especially people who grow a little old, that tend to develop this, eye pressure or increase in eye pressure because of a condition called glaucoma. So what they do is that they basically use a vortex gun to shoot a vortex ring onto your eye and therefore measure the pressure in that particular way. In that process, you also generate droplets because of your tear film in the eye. So there are many applications and, in ways where this kind of thing happens. Then you have droplets at high velocity scales. These are of Mach 3, which is typically close to 1,000 meters per second. But the droplets are extremely small. And we are going to talk a little bit about this in the later slides. So this is called high velocity, small length scales, usually called droplets under extreme conditions. For example, this is a droplet which encounters a shock wave. Then you have the corresponding interactions happening in hypersonics, for example, where the flow is typically close to Mach 5, and therefore you have to understand how the combustion of droplets takes place in those kind of situations. And lastly, there are high velocities and large length scale problems. This is typically what we encounter in your gas turbines and in your other applications. So gas turbine, the typical length scale is of the order of 1 meter. So in this slide, what I showed is basically you have velocity scales which varies from microns per second all the way up to thousands of meters per second, and length scale which varies from tens of microns all the way up to a meter. So you can understand the scale change that happens in these kind of problems. So this is what makes analysis particularly difficult because of this scales of the problem. So fluid mechanics is all about scales of the problem and how these scales actually interact with each other. So in this way, I have also divided my research all the way from small scale to large scale, and you do fundamental research all the way up to applied research. So this is a slide which basically tells you the different aspects of research. So anything dealing with multi-phase systems, interfacial sciences, we actually try to analyze those problems. Okay, so there are certain very interesting problems, some of which you will see in the next few slides. All right, so I'm a fan of Tintin. So what I can tell in this particular slide, that this is like the adventure of a droplet. So if I'm a droplet, so what happens to me is my journey. So I can deform, I can evaporate because I'm a liquid droplet, so I'm supposed to evaporate. I can impact a surface. I can atomize, that means I can break up into smaller pieces. And in some cases, for reacting systems, I can also combust. So these are my different fates, my different destinations. It depends on the applications, but all applications will have one or two or more of these outcomes. So this is my journey of the droplet. My students tell me that we actually torture droplets. But since they cannot speak, so we get away with the situation. All right. So this is the adventures of a droplet. And first we start with droplets in disease transmission. We look at a couple of specific areas which may be interesting to the audience, just given that it is a broad audience. So the disease transmission is something that I'm going to do. There is a little bit of math and a little bit of experiments involved in this. More details can be found in the papers, which I'm pleased to share if anybody is interested. But this we started during the COVID era when there was a lockdown, and I managed to keep my lab open in ISC. So I, along with a couple of colleagues, actually one of them is my student in America and in Canada. The three of us started doing this because there was nothing else to do at that point of time. So that led to the journey of droplets in disease transmission, and we have continued that for other kinds of pathogens as well, not just virus, but bacteria and other kind of stuff. Mainly looking at it from a fluid mechanics point of view. Okay, so that has led to collaborations with biologists, because I don't understand biology that much. So that has led to collaboration with biologists, and we have unearthed some pretty interesting features. So, but this one is less of biology, more about the fluid dynamics of the problem. So we are going to do droplets in disease transmission. So to give an idea that, spread of COVID-19 like pandemics. So you see that there is a population in which the green means these are uninfected people. And suddenly you have one infected person in that population. And after a few weeks, say n number of weeks, the population has lots of infected people. Okay, so this is what happened during COVID. It can happen in other types of pandemics also, which are respiratory related. So the question that all pandemic modelers and other people actually asked is that how fast does the disease spread? I mean, this is a fundamental question, because that will enable us whether to keep hospitals, how many beds we need, what is the oxygen requirement, what kind of lockdown we should have, social distancing, and many other stuff. So the idea is that any pandemic model, so basically tries to predict the rate of infection, and that typically should be a function of multiple parameters. So x1, x2, x3, all the way up to xn. So typically the pandemic models are complex, as you can understand, and it has got a large uncertainty. That's why we did not predict COVID-19 that well. But some of this uncertainty, what we felt was, can be reduced if we used certain physics-based submodels, so that not everything is based on curve fits and stuff like that. Okay, so that led to the journey. So what we thought is that, can we look at small-scale interactions, that means the droplet-level physics, to predict the large-scale pandemic? So you understand there is a small scale where the droplets are typically of the orders of microns, and to predict a macro scale event, which is like a pandemic. So can we derive such a model from first principle and reduce the uncertainty as much as we can? So this is more like a framework development, therefore. So how does the transport happen? So an infected person actually sneezes, coughs, talks, okay, sings, whatever he does. He releases a cloud which is infested with droplets of various sizes. This cloud actually expands, right? Because any system, any cloud or anything like that, it will expand, and a healthy person actually inhales this and becomes infected. I mean, this is the standard methodology. So what happens is that when the respiratory events actually eject these droplet clouds, so it is influenced by various events. Like, for example, if you wear a face mask, this cloud will be different. Now, these clouds are then transported, and at the same time, it is dissipated as well. So because the fluid mechanics systems are highly dissipative in nature, so they are influenced by your ejection condition. For example, your cough cloud will be different than your sneeze cloud. And it is also influenced by the ambient flow field where you are situated. Now, these droplets do not remain intact, right? So they will actually evaporate. They will precipitate, because these droplets typically have salt, and they will aerosolize. So if they aerosolize and precipitate and evaporate, they will be influenced by the ambient conditions like temperature and humidity. Now, ambient conditions like temperature and humidity is very it will influence, because if you have a wet towel, if you want to dry it during the monsoon season, it will dry at a much slower rate compared to if you want to dry it during summer, but or during winter. So it is dependent a lot on the temperature as well as the relative humidity. Now, these inhaled droplets, when a healthy subject actually inhales the droplet, then it is not only the viral load that he inhales, but it also is the biology of the virus. In some cases, if you are dealing with other pathogens, the biology of the pathogen and the immunity of the subject. So even though I might inhale a certain quantity of viral load, and somebody younger might actually inhale a similar quantity of viral load, the outcome may be very different. But so it's a complex subject. So it's not just transmission, it's how it affects the subject. It depends a lot on that. So the pandemic model, initially, we'll come to this a little later as well. So we thought that, because coming from chemical engineering, mechanical engineering, and all other backgrounds, you have a ready-made analogy that you have something like a collision theory, like, in combustion that is very regularly used, like an infected person and a susceptible person gives rise to two infected persons. And this reaction proceeds with a certain rate constant, which is K, right? So it's very similar to like two A and B, two molecules colliding and forming a product, which is AB. So this forms the fundamental principle of ACIR model. So it can be derived from first principles, actually. So what happens is that if you look at a person P, he ejects a cloud of droplet. This cloud goes on increasing in size, and any healthy person, which is designated as H, which comes into this domain of the cloud, right, within this ambit of this cloud, will get infected. So in other words, we are saying that the rate constant at which the reaction is proceeding, or the rate of infection that happens, should be a function of the droplet physics. So this is the basic tenet of what we are trying to do. So the droplet physics, in the case of pathogen, is basically we are dealing with respiratory droplets. So these are essentially multi-components. So they have mucus, they have water, they have salt, and they have the virus. So they undergo, as we said, evaporation, something called dispersion, settling. The larger droplets will actually settle. Then something called evaporative cooling, because as the droplets actually evaporate, they can cool down. And they also has a phenomenon like crystallization, because they have salt, so they can crystallize. And their lifetime of these droplets is a function of the relative humidity and temperature. Now, these exhaled droplets, they actually suffer three fates. They can remain droplets when they reach you, when they infect you. They can transform completely to nuclei, which is basically completely evaporated droplets. So all you are left with is a solute. They can also settle on surfaces, which we call fomites. That's why we used to, desanitize or sanitize our Amazon boxes and our parcels and all those things. So all these three can actually cause infection. So these are infection pathways, essentially. So the goal of this study was that you develop a methodology to do this. So how do you do it? You first do some experiments with isolated droplets. Then you model the transport process, and then couple that model to a pandemic model. These are the two things that you can do. And then look at other stuff like fomites, and when you have face masks, what happens and stuff like that. So we are going to take the first three. The fomites is a huge area of research where we have done significant amount of work, but we will take that in some other session somewhere in the future. So experiments with isolated droplets, how do you do it? So the evaporation pattern is very important. The precipitation dynamics is very important. So you basically simulate the respiratory fluid. So typically you use 1% aqueous NaCl solution as a surrogate respiratory fluid. You also add nanoparticles, which are typically 100 nanometer in size, as a virus substitute. You otherwise would need a BSL-3 facility to carry out the research. That also we have done, but at a later stage. So, but this is good enough to understand the physics of the problem. So what we use is an acoustic levitator. So an acoustic levitator is something where the droplet can be anchored in a contact-free environment using nothing but the acoustic forces. And we use high-speed shadowgraphy and laser imaging to see what is going on with the droplet size and the final precipitation morphology. So, and we have done varieties of things. We first do a control case with pure water, then you use NaCl water, then you use NaCl water plus nanoparticles, just to see that what are the effects of different components on the overall evaporation dynamics. So this is what happens. There is a first stage during which the droplet diameter just reduces in size. As you can see from left to right, it reduces in size. Okay. At a certain time T1, the diameter reduction ceases, and at T2, because the salt actually goes to the surface, so the diameter gets locked. It no longer shrinks any further. And at T2, you basically have the precipitation event happening. And depending on the different viral loads, you can see the different states of the precipitate. They are all looks very similar. Okay, so this is the completion of precipitation. All right. So if you do pure water, okay, you can get something like this. It follows something what we call a d-squared law, which is a diffusion-dominated phenomena. And it roughly takes whatever time, whatever is the diameter of your droplet, it will scale according to that. And then if you add salt water now, the evaporation is a lot slower just because of the effect of the solute. And this is governed by Raoult's law. And as the salt concentration increases, the trajectory, this d by d naught curve, tends to develop a knee. So the evaporation actually shallows down. So it is a question of evaporation rate weakening. Okay, but when you add nanoparticles to it for the kind of viral loadings that we are dealing with, there is no change. So there is no change in the evaporation curve, and the precipitation for the kind of salt concentration we are dealing with triggers at around 0.2 of the initial droplet diameter. So this is where you get the knee and the droplet doesn't shrink any further. All right. So this is at a typical temperature and relative humidity setting. So this slide I will just skip. So this is what the precipitate actually looks like. So in shadowgraphy, you will get these morphological changes of this precipitate. We also use laser scattering to identify the solidification front. You don't see a localized solidification. You get this more of these crystals that actually forms. You can take it to a confocal microscope or a scanning electron microscope, and you can see that all these virions or all these nanoparticles are basically embedded within the crystal. So it is basically a fossilized. So all the virus are basically fossilized within the crystal. So when you actually inhale an aerosol, you are basically inhaling a dose of this crystal, which is infested with these virions. But the virions are in a state of, are basically fossils. But what happens when it goes into your mouth, it rehydrates itself and they come to life. Okay, or if you consider the virus to be living in that way. So what we can say is that the presence of the salts affects the evaporation, and nanoparticles does not affect the evaporation, and the nanoparticles, aka the virus, distributes inside the crystals that forms at the end of the evaporation process. So these are the insights from the experiments. So now it sets the stage so that we can go for the modeling aspect of it. So it has to be a physics-based model. It has to be validated by the experiments. It should capture the effect of the ambient conditions as well as the jets that are coming out of your mouth. But at the same time, it should be simple enough to use in large-scale pandemic models. See, we ourselves have done modeling of droplets, which are very complicated. You can solve for the entire field within the droplet, outside the droplet, etc. But to incorporate them in a large-scale pandemic model for a quick turnaround time is vitally important as well. So you capture the essential physics, but at the same time, keep it light so that it can run pretty quickly. So again, we used the same NaCl solution. No need to model the virus because they don't have any effect on the transport and the lifetime of the droplet. So the approach is basically a Eulerian flow description with a Lagrangian droplet coupling, and so one-way coupling. And we have like a homogeneous droplet model, as well as we have 2D models, we have 3D models, lots of things. I'm just going to show you the very basic model here. So the model has got 4 components to it. First is to model the respiratory jet and the puff that is coming out of your mouth, and then the aerodynamics of the droplet, that's how these droplets gets transmitted and how they are controlled by the jet and the puff. And then, of course, the heat and mass transfer of the droplet, because these droplets shrink, as we saw. And then also trying to understand the precipitation physics and do all these things in a simplified fashion. All right. So this is the respiratory jet and puff. So this is what comes out after a violent coughing incident. So you can see the picture on the top right-hand corner. And so when we cough, we first generate a jet, a turbulent jet. But any jet actually requires a constant momentum source. But we don't cough continuously, right? We stop. So as soon as we stop, the momentum source is cut and the jet actually transforms into a turbulent puff. And we have modeled both aspects of it. So you can see the equations, not going to go into the details of the equation. And this puff bed therefore shows an expansion, as you can see. R is basically the expansion of the puff, and it is how it scales with time. And here time also means distance. So how it actually expands with time and distance. That is what is shown over here. Now, the aerodynamics of the droplet is rather simple. So you have the droplet motion, which is basically the same as the motion of your aircraft or any other things that you can think of. There is a coefficient of drag, and then there is a velocity, the relative velocity between the gas phase and the droplet phase. So that is what governs the motion in the x direction, but there is a y direction also, which is basically controlled by the Stokes settling velocity. So these droplets actually, they go in the x direction, which is in the horizontal direction, and they also fall just because there is gravity. So, but smaller droplets can stay forever in the atmosphere. So now, once these things are done, then you have this slightly complicated model where we actually model the evaporation, and then we model the droplet size reduction, then we model the crystallization, and we also do an energy balance of the droplet surface. So all these things should give you that what is the diameter reduction time, how much time the droplet takes to form the nuclei, and how much distance it should actually travel, and what is the the total diameter of the puff by the time the droplet is completely evaporated. All right. So forget about the technicalities of some of these terms like the Sherwood number and Spalding mass transfer number. So these comes you have to know a little bit of the evaporation and heat transfer aspects of it. But these can be all solved, and you can solve it in a desktop using a MATLAB code. So no problem there. So you can easily do it. And then you match it with experiments. So you get a good agreement to the experiments. As you can see, we're able to predict the right for different droplet sizes. As you can see, 300 micron and about 650 microns, we are able to model both pure water as well as NaCl with a great deal of agreement. Okay. So and then we can reconstruct what we call a modified Wells curve. So what we can say is that the small droplets evaporate quickly and remains airborne as nuclei. So the small droplets, before they settle to the ground, they evaporate and remain airborne. The larger droplets actually settle quickly. As soon as they come out of your mouth, they will settle around you. So the chances of infection actually grows when the droplets are small. This needs to be clearly understood. The small droplets are the ones which causes the havoc. Okay. Now, if you forget everything about the model, these plots should be pretty interesting to look at. So for example, if I look at the plot on the right hand, that means the right hand corner, that means the fourth of the four plots that I am showing over here, this shows that with relative humidity of the ambient and temperature of the ambient, how does the droplet lifetime actually varies. So you take two locations, A and B. So A is in a location where the temperature is very low, okay? And the relative humidity is kind of, in the 50s. So you go to a cold place, which is a lot less humid. So A will say that what is the kind of distance that the droplet travels before it becomes completely aerosolized, all right? Now, let us take point B, which is another location where the temperature is, is kind of 25, 27 degrees Celsius, typically like Bangalore weather, but the relative humidity is rather high, so it goes up to 80. So in those cases, you can readily see that the distance that the droplet travels is much more. So you have a situation where you can see that the droplet lifetime is much higher, is maximum for high humidity and low temperature, okay? And this allows, so that means when the temperature is low, and the relative humidity is high, typically in situations like maybe seashores or something like that in cold places, the droplet travels one order more. Okay, so the droplet lifetime is one order more, and it travels a distance which is much more than the 6 feet distance that normal was a recommendation during the COVID era. Because you can see these are given in meters, so it can go anywhere between 2.5 meter all the way up to about 4 meter. So this tells you that if you use modeling, then you don't have to be arbitrary in your understanding of the situation. Okay, and the droplet lifetime, which you see in the plot just above it, there you can see that lifetime varies anywhere between 3 seconds all the way up to about 27 seconds. So it's like one order change in the droplet lifetime. So the understanding from the modeling was that cold and humid weather extend the droplet lifetime significantly. Okay, and respiratory droplets at certain weather conditions can travel more than 6 feet, and the droplet nuclei can survive and travel much more than the droplet themselves. So now we come to the pandemic models. We understood the droplet physics. We now understood what is the lifetime and stuff like that. So this is called the SEIRD model from the collision theory. So it is thus given as three equations, so to say: susceptible, interacts with the infected to form exposed and infected. The exposed becomes infected over a certain period of time, and the infected, either they recover or they die. Okay, so the mortality rate was typically 3%. So that is the ratio what you see in the R3 equation. And your K1, which is basically the infection spread rate, has to be more than K3, that is the recovery rate, for the pandemic to grow. And so some of these are taken from the experimental findings and the commonly associated knowledge. Now this alpha and beta that you see, so alpha can be the type of respiratory event that we are talking about: coughing, sneezing, breathing, etc. And beta can be the mode of transmission, which is like the droplet nuclei, fomite, and you can have whatever that you want. So this is in principle what is the model all about. And this is based on that there is a droplet cloud, the cloud spreads, and anybody who comes into the ambit of it will actually get infected at a certain rate. Okay, so to cut a very long story short, you can do like 3 pages of math and show that the infection rate, that is K1, is given by that equation that you see over there on the screen. Out of that sigma ds that you see is the spread of the droplet cloud, which comes from the droplet model, which we showed already. This is the aerodynamic model. And then you have a VDS, which is basically the velocity of the droplet, which also comes from the droplet model. And then you have a generalized probability of infection, which is also dependent on the half-life of the droplet, viral load, the droplet cloud, frequency of the respiratory events. That means how many times you are coughing, sneezing, etc. So together, you can now calculate the infection rate constant. So it comes. So as you can see, all the things that you see within the integral comes from the small scale droplet level physics. All right. And this is like a typical infection probability from a cough event where the temperature is about 22 and the relative humidity is about 50, typical Bangalore weather once again, where you can see, if you look at the curves, so D, the red colored curve, basically designates infection probability from a droplet. And N, which is the blue curve, designates the infection probability from an aerosol or from a nuclei. And the black curve is basically the combination of both. So as you can see, when at small time instances, that means when a coughing event has happened, or if you are in the proximity of the person where that coughing event has happened, the probability of infection is quite high, and it primarily comes from the droplet mode. The aerosol mode typically kicks in a lot later because the droplet has to become aerosol. They do not become aerosols as soon as it comes out of your mouth. So they will require a little bit of time before they become aerosol. And these aerosols typically are a late acting event, but they have a longer lifespan. That means the time is long. So that means you cough in a room and you go out. Somebody else who has never faced you enters the room after some time and can get infected due to the aerosols. So it is not just a direct transfer that I cough near you and you can see the person and you get infected, but it also can happen that you have coughed and you have formed this droplet cloud which is aerosolized now, and they can actually lead to infection at later time instances, which also means that it can go to for later distances, higher distances. So this is the infection probability. So you can see initial risk from the droplet is high, but the risk from the droplet reduces after a certain time as they settle or as they desiccate, but the nuclei remains airborne for a longer period of time, causing havoc. All right. And then you can reconstruct all these things from the ACIR model, and you can show that how the infections will actually propagate over a period of time. So like a typical 100-day evolution of population. Now, we have also shown that if you use a mask where you actually are cutting down on this, on this cloud generation, you can actually lower the infection count or the infection concentration by quite a bit. And this is exactly why people advised you to use mask. But there is a little bit of a twist in the story, which I'm going to narrate next. And this is particularly true, not just for India, but for any other countries. Well, America may have suffered for some other reason, but but I will give you a generalized description that why masking can also be dangerous in certain ways if we do not do proper masking. So, but let's finish the the pandemic model that we have shown that how the pandemic model can be derived from first principle, and we have established a framework. Now you can make it as complicated as you want. And we also have given some, some idea that how the infection will actually propagate. So the masks we also showed they can lower the infection rate, but there is a twist in the tail, which is going to come next. And we all like twisty thrillers, and I am no exception. So I'm going to narrate the mask story, which is next, so which is the story of face masks. So we all know that if you put a mask, basically the jet does not happen. And it also, absorbs some of the droplets. So therefore, the droplets do not go out. So it stays within you. And as a result of that, you can flatten the curve, as they call it. So this was the general notion that how the masks can help the purpose and the effectiveness of the mask. But we wanted to look at something important, that what happens to individual droplets when we actually have a sneezing event or a coughing event. So what we did was that we had a mask which we clamped, and then we used a pulsed laser, and we used a droplet dispenser, which basically used surrogate respiratory cough droplets, typically about 1% by weight of NaCl, about 0.3% of gastric mucin, and certain other components. And we varied the droplet sizes, especially the larger ones, anywhere between 250 microns all the way up to more than a millimeter. So, and typical experiments that we are going to show over here is about 600 microns. So you basically let these droplets impinge on the mask at velocities of 2 to 10 meters per second. So these are the typical velocities with which the cough droplet comes out of your mouth. So, so this is important. In a sneezing event, this velocity is even higher. In fact, a sneezing event velocity can be as fast as a Shoaib Akhtar delivery. So it can be of the order of 150 to 160. Okay, so let's look at this particular incident and see. So your mouth actually lies where the droplet is getting dispensed, and the mask is basically trying to protect your mouth. So basically the purpose of the mask is not to let the droplet through, right? Because if it lets it through, then what's the point of wearing a mask, right? So we tested two types of masks, so locally supplied and the medical grade mask that you all have. So we used a single layer mask. So single layer mask looks like this. And if you have a double layer mask, it looks like this. And then if a triple layer mask, it looks like this. So, and this is the scale. This is about 500 microns. The typical pore sizes are of the order of 30 micron, 17 micron, and 12 micron, something like that. This is just a generalized picture. So let's see what happens if you can watch the video. Let's look at a single layer mask, and you are coughing from the side the droplet is coming from. So what do you see? In a single layer mask, a large droplet falls on the surface, and it gets extruded through the mask, and it forms many, many daughter droplets, which are of much smaller size. The double layer mask does a better job. And the triple layer mask does an even better job. So when we talked about triple layer masking and other things, okay, there was some logic into it, not necessarily this logic. Okay, so what we see is that we have penetration, we form what in fluid dynamics terms called ligaments, and atomization into smaller droplets. Got it? So there is a criteria. You can work it out. As we see, the fluid mechanics deals with scales. So if you have an estimate of the initial kinetic energy of the droplet, and if you can calculate the energy of dissipation as it traverses through the mask thickness, you can have a penetration criteria, where essentially what you mean is the kinetic energy has to be much, much more than the dissipation energy. And from there, you can calculate the Reynolds number, and you can show that there is a penetration criteria. Interestingly, this penetration criteria is independent of the droplet size, but only dependent on the impact velocity, because you don't see any mass terms over there. All right. So the experiments we did with various velocities and stuff like that, and indeed you can see initial droplet diameter. So the impact velocity and the size, you can see above a certain impact velocity, all the droplets actually penetrates. All right. Now, this is the most important thing that you will see, that when you have a droplet impingement on a mask, then what we do is that downstream of the mask, we measure the droplet sizes. So as you measure the droplet sizes, then you can construct a PDF of the droplet size distribution. Now, what you can see over there is that the peak of that particular distribution for a 620 micron droplet is under 100 micron in diameter. So 100 micron droplet, smaller the droplet, it can aerosolize even faster. So the large droplet, which is half a mil, which would have settled to the ground around you and would not have caused that much infection, is now getting aerosolized or atomized into smaller droplets, which are less than 100 microns in size. And these less than 100 micron droplets, as they come out of the mask on the other side, will actually aerosolize and cause more damage. All right. So this is true for both water as well as surrogate fluid droplet. So this is what we actually get, and this is like a amazingly, dreadful situation. So poor mask quality pushes the PDF towards the smaller droplet sizes. Therefore, smaller droplets can evaporate and aerosolize. They can travel longer distances. Therefore, their infection, circle will be much, much more compared to larger size droplets. So improper masking is bad. Then we did the same thing for various homemade masks, and this is where we say that in India it was very common because people used handkerchiefs, they used cotton towels, gamcha essentially. They used lots of other things in the villages, some of which has got large ports, some of which has got small ports, etc., etc. And we did a lot of studies, and we came up with a two-part criteria that how cloth masks can be useful or not. And one of the criteria you have already seen, that is due to the viscous dissipation. The other one is the resistance due to the surface tension effects in the pores of the mask. And once you have all these criteria satisfied, the droplet can penetrate. So normally when you have something called kinetic energy much higher than the interfacial tension, you will have the droplet which will go through. Okay. So in the cloth mask, we found something very similar. So we had the port size, we had the porosity, we had the mask thickness, everything we took into consideration. And, to cut a long story short, even there, we saw that there was a lot of aerosolization that goes on if you have a mask which has got large pores or which has had increased porosity and stuff like that. So this was very common. And that means improper masking, using of makeshift handkerchiefs and stuff like that was actually not a very good thing to do. And we also looked at the washing of the mask, because in India, we used the mask, we washed it multiple times and used it. But obviously, after 70 washes, we did not see much of a change in the aerosolization. Okay, so that was a good, that was a good thing to see. So this was the story of the face mask, that that improper masking actually leads to aerosolization from large droplets, and it generates small droplets, and small droplets can be deadly. So that was the whole idea. That was a good part, and how makeshift masks cannot do a very good job compared to 3-layer masking, 5-layer masking, 7-layer masking, whatever we have seen during the COVID times. Okay, so this is also valid for the rural areas where, buying surgical masks and other things was not very common. So people used whatever they could get hold of, any piece of cloth that they could get hold of. Okay, so we have covered this part of the story, and I think some of you were also interested in the drop atomization part of the story, which is another thing that we do in our group quite a bit. So I will just take some time to finish this, roughly another 10 minutes or so, if I can go quickly, and then study this drop atomization and kind of show that what can actually happen in the drop atomization. So this is, for example, vortex droplet interaction. And, this is a breakup event that actually happens of the droplet, but this is very well behaved event, and it's a low intensity atomization, as we call it. You can get a gas turbine situation. So what you see on the left top corner is basically a spray, a sheet, which is flapping in a highly turbulent flow, and you generate droplets of spectacular sizes. And the green picture that you see in the middle is a high-speed PIV, the high-speed flow visualization, along with the droplets, and it shows that how the droplets gets deflected and how they get atomized at the same time, and how this atomization actually happens over certain scales. So this is what we call a moderate intensity atomization. Then, of course, some of these things we have seen earlier, probably, that this is a droplet which is encountering a vortex. And you can see the shape of the droplet that happens. It resembles basically Harry Potter's Dementors. So it's a Dementor, but this is also a moderate intensity atomization, as we call it. But I just wanted to show you a few things about droplets under extreme conditions. Now, extreme conditions, normal real life scenarios are all extreme. So for example, if you have a liquid jet in a supersonic flow, if you have a drop impact on a Mach 3 missile, and the third picture that you see is basically how we generate metal powder for additive manufacturing using something called a closed coupled atomization, where you can see shocks and expansion waves all around. And then you have this sheet atomization phenomena that I showed a little earlier. So the droplets atomize, and they atomize in a catastrophic fashion. Okay. So this is what happens. So you have a primary atomization stage where you generate the first generation droplets, and then you have a secondary atomization stage where you generate the droplets into further daughter droplets, which goes into the refinement of the spray pattern. You ideally need the droplets to be small so that you enhance heat and mass transfer or combustion or whatever it is that you are trying to do. So these are the basic fundamentals. And it has only a few forces that you can think of. You have the shear force, you have the pressure force, you have the body force, you have the capillary effects, and the viscous force. And as fluid dynamics guys, we actually go by our non-dimensional suit of numbers. So Weber number is the inertial force divided by the surface tension force. Then there is something called Onsorge number, which tells you how much the viscous force is important. And then you have the standard Reynolds number, which is inertial versus the viscous force. So these are the three normal numbers that people deal with all the time. Now, normally, when you actually isolate droplets, you actually have a very strange gamut of features. So when the Weber number is low, that means the inertial force is not very high. The droplets actually vibrates and breaks up. So you can see this very nice vibration patterns. A slightly higher Weber number, you have something called a bag. So it's like a balloon. It just swells up like a balloon and then it atomizes. Then you can have a balloon with a stamen. Then you have something called a sheet thinning, and then you have something which is called catastrophic. All right. So this is for example, a bag type breakup. Just look at it. You can see it swells up like a bag and then it atomizes. Okay. This is around Weber number of 12. Then you have the bag and stamen, and it atomizes. This is around Weber number of 44. Now, then you see here the sheet thinning. Do you see the sheet coming out from the sides of the droplet? So this is around Weber number of 205. And then at Weber number of 14,000, literally the hell actually breaks loose, and you have something what we call catastrophic breakup. All right. So people have been able to do what we call a regime map, in which we say that how the droplet breakup varies with Weber number and Onsorge number, basically viscous effect versus inertial effect. And it can be shown that for a large range of viscosity, basically the viscosity doesn't play any role. It is only the Weber number which basically dominates the show. So, and this is based on mostly bucketing the droplets in terms of the topology of the breakup. Okay. But this is actually not a good thing. It is only based on the topology, nothing else. It lacks the physics-based intuition, and we sometimes call events like catastrophic, which is a vague interpretation of the matter. Okay. So first we look at the mechanisms by which an interface actually destabilizes. So one side can be liquid, one side can be gas. So there is something called a Rayleigh-Taylor instability, named after Lord Rayleigh and G.I. Taylor. So when a lighter fluid pushes into a denser fluid, you get a pseudo body force, which originates from the interface acceleration. As a result, the interface starts to curl up, and this interface gets destabilized, and you get this atomization, or it basically, dissociates. Then you have something called the Kelvin-Helmholtz, which is basically due to the shearing action. So if the two fluids move at a certain relative velocity with respect to each other, which basically shears with respect to each other, you have the Kelvin-Helmholtz instability. This you see in atmosphere also. And you see it in very small scale, you see it in atmosphere, you probably see it in the astrophysical scales as well. And then lastly, you have the Rayleigh-Plateau instability. It is due to the capillary action of the interface. This you see in your kitchen sink. If you have your tap open just a little bit, you'll get that filament that comes out, and then it destabilizes after a certain distance, and it forms this ligament. So these are basically the three mechanisms by which the interface can get destabilized. So what we found out, that for a droplet which experiences a very high speed flow, first there is deformation, just because there is a difference in pressure between the fore and the aft of the droplet. Okay, so there is a wake region that tends to form on the other side of the droplet because of flow separation, and this droplet therefore deforms. Now, if there is Rayleigh-Taylor piercing, so it will form this kind of a structure, which is a bag and stamen kind of a structure. And this wavelength is basically given by the Rayleigh-Taylor, instability wavelength. Or you can have this Kelvin-Helmholtz waves, which accelerates and goes towards the equator. They merge, they form this sheet, and this sheet actually breaks up into pieces. So this is what we call shear-induced entrainment, which is dominated by the Kelvin-Helmholtz mechanism. So the initial part, the first few breakup modes are basically Rayleigh-Taylor piercing. The last few breakup modes are called the shear-induced entrainment. Actually, if you look at these extreme high-speed images that were taken, you can actually see the Kelvin-Helmholtz waves. You can see the sheets. You can see the ligaments. All of it is a part of this whole situation. And not only that, though the Kelvin-Helmholtz wave actually prepares the ground by creating these undulations, the azimuthal Rayleigh-Taylor instabilities and the longitudinal Rayleigh-Taylor instabilities basically are superposed on this Kelvin-Helmholtz. So basically you have a combination which is shear-induced entrainment, but there is also an effect of Rayleigh-Taylor piercing as well. So it's a complicated breakup mode that we talk about. You can also have compressibility effect, that is due to the high Mach number of the event. And you get things like bow shock and stuff like that, which leads to non-uniform flow situations. And it actually gives rise to this kind of situations. Okay. So this led us to the formation of our map, which is now called the Rao Basu. Rao is my student, basically. So in this map, we categorized things using the instability modes, which is much more prudent than to do with a topology-based mode. But this map was still static, and it was unable to capture the unsteady, topology, how the droplet actually deforms and goes bad. Okay, so that is what is up next. So the breakup of the spatiotemporal scales and the cascade behavior of these deformations. Okay, so how to do this kind of experiments? You actually can do it in varieties of ways, but since the time is short, I'm going to show only the shock tube part of it. because shock tube is what actually guarantees you to generate very high Weber number, very high flow. You can do it in a continuous jet, you can do it in a drop tower, many things are possible. We have done it across all kinds of states, but shock tube is the one that generates the most impact. So this was our custom shock tube. And if you look at the picture on the right hand side, this is what the flow actually looks like. It's horribly complicated. And you have a zone of interaction and you have a compressible vortex ring. So these are a lot of technicalities, and the white dot that you see is where the droplet is placed. So you have the shock directed towards the droplet, and we can actually image this with extreme high fidelity. And this is what the shock tube looks like in the lower two pictures. So this is a patented piece of information, and you can go up to a Mach number greater than 3 and a Weber number of approximately 10 to the power of 5, which trust me is very, very high. Okay. So this is what happens when the droplet actually encounters the shock. Well, it does not show anything. It just shows the reflected shock and stuff like that. But when you actually, what happens is that the flow that is entrained or induced by the shock, which is called the compressible vortex ring, that is what interacts with the droplet and causes havoc. And this is what happens. For low Weber number, you will get the Rayleigh-Taylor piercing, and for high Weber number, you are going to get this shear-induced entrainment. All right. So this is how it looks like. You can take a look at different Weber numbers, how they look like, how the liquid sheet actually gets stripped, and stuff like that. Okay. So this is called KH instabilities. So if you do linear stability analysis of this, and if you try to model this, that whether you can predict the correct wavelength that are the most dangerous wavelength or the fastest growing wave number, whatever you call it. So this happens because there is a slip at the interface. I mean, normally people do that. There is a slip at the interface, but which is unphysical. So that does not give you a good prediction. But if you take into account the boundary layer, which is basically you take into account in other words, the vorticity layer thickness, that means the boundary layer over which the flow actually gets modulated, then you get a pretty good match with the experimental and the numerical and the theoretical data. So it's a much better match. You can do the same thing for RT waves, the Rayleigh-Taylor waves, and you also get a pretty good match between the experimental and the theoretical models. All right. So this predictions match in an order magnitude sense. Okay. So I will just skip. I will just go to something which is a little bit more interesting, because these are a lot of technical details. You can also show that all the droplets actually break up in a similar fashion. So we have done it with the data that we showed are for Newtonian liquids. Now you can go to polymeric liquids. So you can see the polymers. The middle one is the polymer. So you can see these tentacles that are coming out. And the lower part is a liquid metal, which is Galstein air. That also shows an atomization. But if I remove the labels, you will see that the atomization physics, that what induces atomization, is the same for water, polymer, and Galstein air. Okay. So that is the most important part. And, whatever is the concentration of the polymer, the way the instabilities develop is basically the same. Okay. So what we did is that we got a temporal map, which says that in stage 1, if you look at it from left to right, you have a droplet. First it deforms, then it forms these KH waves or KH and RT waves, or it undergoes vibrational or Rayleigh-Taylor kind of a mode. And at stage 3, it forms all kinds of structures depending on what kind of liquid you are dealing with. So the first 2 stages are universal. The last stage, which is basically the final topology, that actually is different for different fluids, but the instability mechanisms are still the same. So you can put all these things in a temporal regime map, where you can say that how the droplets actually proceeds from one stage to the other, what is the pathway basically it takes, and how it ends with the end state. And the fact that the first 2 stages are the same across any type of fluid that you are actually dealing with shows that this is a universal framework, okay, for the same. Okay, so this is also liquid metal atomization that we have. So this is the story in a nutshell. So I'm in the next maybe 5 minutes before I end this particular talk, we are going to see something even more interesting where we look at the multi-scale physics of the problem. That means how the evolution mechanism actually works. So if you look at something like a catastrophic breakup, it's messy. You see nothing but a mist and a cloud of droplets and stuff like that. But if you look at the stripping mechanism in details, so this is a droplet which initially deforms like this. And then there is an incoming flow, which comes with a velocity, and then there is an oscillating component to it. So now you see when the droplet has deformed and the first round of wavelengths have formed around it, this now starts to modulate the incoming flow. So in other words, the deforming droplet starts to modulate the airflow by forming these small vortices along the crest. So these are like small hills that starts to form on a curved interface. So this is a typical two-way coupling that you have. Now this interfacial waves actually starts to modulate the local aerodynamic forces. Now if you take a small portion out of it, you will see that there is a local Weber number, there is a local deformation length scale, and the droplet atomizes and it exposes a fresh surface to the same kind of disturbance. As a result of that, it's a local physics that basically controls this breakup that actually happens. All right. So the waves, therefore, in fluid dynamics terms, undergoes a cascade, which eventually fragments and generates new surfaces, and this process goes on and on and on and on. All right. So this is how this actually stage happens. You can take a even closer look at this. So you can see that this is a droplet. Initially, there is a wake around it. The droplet deforms, the wake becomes enlarged. It becomes even more enlarged and starts to form the first generation droplets. Now, if we take a look at this portion here, it is curved. And you can see that locally the speed is changed. As a result of that, the sheet gets stretched in the direction. And because the sheet is getting stretched, if you look at it from the top view, this actually leads to what we call a Rayleigh-Taylor waves. And then it forms these local bags. So these bags are not global bags. These are local bags. And it generates droplets at the end. So this is what we call a ligament-mediated mechanism transfer. So this is what we call the subsecondary breakup processes. And it actually has a self-similar behavior. Okay. So this is what happens, and I will show a couple of images basically to prove the point that what happens in the case of droplets like this. So you can see actually that how this bags actually form. All right. So this is always a ligament mediated cascade at the end of the day. So this is what you see. So these are like small bags, what you can see over here. Remember, this is the scale. So the droplet scale is, say, 0.5 mil. But these scales that you see around in the zoomed in views that are very, very small, and they locally form these bags and rims and stuff like that. Okay. So this leads to what we call a ligament mediated droplet generation. And to cut a very long story short, okay, we don't have time for that. Okay, there are new optical techniques that we also found. So let's not bother about that particular story. We can actually show that the droplet size distribution actually shows a self-similarity if you do this calculation properly. All right. And to go next, you can see that you can explore these ideas further. And the next thing that we are trying to do is develop, turbulent multi-phase system scaling laws for the same. So for turbulent flows, we have certain scaling laws, as we all know. But can we do that for the droplet, for this cascade behavior, and kind of try to understand the turbulence mediated energy transfer to the droplet level and vice versa. Okay, so that is a task for the future and ongoing kind of work, and also to work with other types of complex fluids so that we can understand more about the breakup dynamics. So there are lots of things. I will stop kind about here, okay, because there is also a story on evaporation and self-assembly of droplets, which we are not going to go because that is a story. This is a very long session. It will become otherwise. So I will stop the talk now, and anybody who is interested in asking any question, I will leave it up to them to now come on and ask. Thank you so much.
Yeah, thank you very much, Professor Saptasi Basu. We don't have much questions, but your talk was really marvelous, uh, and you
Thank you.
touched different scales of droplets, and I'm very much sure that student will be it will be helpful for the students. So let
Yeah.
us stop over here. I'm especially interested with your
Hmm.
talk in the sense that your study is it's works for the different scales. So since I
Yes.
work with the astronomical scale, so it's a very big in comparison to the droplets you worked, we found that for the case of the radio jets, the we have
Hmm.
there's a jets and it's a sock and sometimes we have lobe kind of things and it's a multi-parsec scale the structures happens, but
Correct.
the
Correct.
pictures sometimes the pictures looks more the same. So maybe
Yeah. Yeah.
the some of the physics are same, uh,
Yeah. It's
and
most of them are same. Yeah. Yeah.
yeah, yeah,
In
yeah,
fact, if you look at astrophysical scales, if you look at dispersions and other type of events, you can actually, for the turbulent jet or for the turbulent physics, you can actually, scale them in a very similar way. So I mean, the fluid, the only thing is that you are dealing with different, non-dimensional numbers, but
yeah,
mostly the physics will be the same. So there should not be any problem, at least on the dispersion and the shocks and the jets that you are talking about.
yeah.
Yeah.
Now we have a question from uh, Utpal Babu. So I'm just showing it to the screen. Uh,
Hmm.
a lot of
Hmm.
detailed work involving what seems like nonlinear equations and therefore
Hmm.
highly dependent on initial conditions and other
Yeah.
parameters. Are there generic macroscopic descriptions?
Yes, so some of them is what we were trying to find out. So, for example, turbulence, there are certain energy cascades, certain scaling laws that you can derive, okay, and which shows that what is the general statistical behavior of the systems. Similarly, in the case of droplets, also like the self similarities that we talked about towards the later part. So, those are also similar things where you can extract, how the system is supposed to behave, okay, certain features of the system. But he's right, Utpal Babu is right, that because these are nonlinear systems, and basically fluid mechanics is nonlinear to begin with, because the advection term is nonlinear. So therefore, you will have systems which will, bifurcate, which will go to chaotic states. Okay, and so we are not, but there are certain features that you can extract, the statistical features. Okay, so some statistical analysis of the same will be valid. So these are all active areas of research. It's very complicated problems. As I said, fluid dynamics is a problem in which you, as I said, from micron all the way up to say meters, and similarly in the scale of velocities as well as space. If you have that kind of a variation, your problem becomes virtually intractable if you try to solve it in total. It's not, people do direct numerical simulations and stuff like that, but in complicated geometries like this, where you have to also resolve the droplet as well as the flow, it becomes very significantly difficult. So there you need physical insights. You need, out of the box thinking, creativity burst to solve this kind of things. So, but there is no generic macroscopic definition or macroscopic framework that actually universally works. So that's why you don't call it a law anymore. There are no laws per se. There are scaling arguments.
There's another question from Utpal Babu. I'm just showing it in the screen.
Yeah. Such approaches, so no steady state. Well, it can be statistically steady or statistically stationary. Things like that can actually happen. So And okay, so this is a topic for maybe one-to-one session also, where we can talk about that what is statistically stationary and how fluid mechanics problems can be cast in that particular way. But the problems that I showed in the droplet breakup, yes, they are essentially non-steady to begin with. Okay, so but these are impulsive phenomena. I mean, these are impulse. I mean, this is a droplet facing an impulsive force essentially. So that's why it would never be steady. But there are situations where you can actually have steady state, again statistically steady state phenomena. Okay, but one has to remember that real flows like turbulence is always 3D and almost always unsteady.
Yeah. So there are different kind of scenario can happen. So one cannot draw
Yeah.
the one prescription for all the cases.
Yeah. Because you see, in the turbulent flows or any kind of flows, the fluid mechanics terms actually, because there is vorticity, we have in turbulent flows we have vorticity production events. Okay, so these happens, because of the production events, the flow is never 2D even. So 2D, statistically two-dimensional turbulence flows are there, very, certain scenarios only. But normally turbulent flows, especially with multi-phase kind of things where you have interfaces, is particularly tough because you see you have a flow which is non-linear. Then you have these droplets, which basically has interfacial physics around it. That means there is surface tension, viscosity, etc. They also deform. They extract energy from the system. They deform and then they break, and they can also add energy to the system and stuff like that. So it's extremely complex.
Complete.
So again, it's a scale. So when you look at the flow around the droplet, it can even be laminar, because at the droplet scale, sitting on the droplet, you see the flow around it to be highly laminar, because it's the relative velocity that you're seeing. Your reference frame is sitting on the droplet. But there can be situations, so from an outsider, it might that droplet and the flow both are moving very fast. So that's how you reduce the problem. So from a droplet perspective, you can describe the flow as unsteady but not turbulent essentially. But then the flow which is away from the droplet can be analyzed in a different way. Okay, so it depends on what you are trying to do and how you are trying to do. Yeah.
Right. So thank you very much, Professor Saptasi Basu, and I am sure that students have enjoyed the show and they have learned a lot. And we will come back again. The Bigyan Chacha Asur will come back again with such uh, important sessions very soon.
Yeah.
Uh, with this, we are ending this session. Thank you, everyone.
Thank you. Thank you so much. Thank you. Bye. Bye.